Imagine walking into a digital museum, where you can ask an AI anything about a 2,500-year-old Greek vase. Not just what shape it is, but who painted it, what myth it depicts, and how do we actually know that? It sounds like the future of cultural heritage. But in practice, vision language models keep failing here. They either hallucinate confident-sounding historical facts when the evidence is thin, or they drown in low-quality search results when you try to ground them in real archaeology. Today, we're breaking down VaseMuseum, a new inference-time multimodal agent framework that solves exactly this problem without retraining the underlying model. The core problem with cultural heritage AI isn't visual recognition. Ancient Greek pottery requires cross-referencing vessel morphology, iconography, production techniques, and provenance. When you ask an open-ended question, the model needs fine-grained visual grounding paired with specialized curatorial knowledge. But here's the catch. Retrieval augmented generation often pulls in weak sources, duplicate snippets, or unverifiable citations. Worse, when evidence is incomplete or scholarly consensus is divided, standard VLMs double down. They output fluent, overconfident answers instead of admitting uncertainty. That's a non-starter for museum applications, where citation validity and calibrated confidence matter more than raw accuracy. To fix this, the researchers built VaseAgent, the reasoning core of VaseMuseum. Instead of treating external knowledge as text to be copied, VaseAgent treats it as evidence to be audited. The pipeline runs entirely at inference time and consists of 3 tightly coupled modules: iterative DeepResearch-style retrieval, source-level control, and response-level reliability calibration. And when you have extra compute, it adds a training-free GRPO-style selection mechanism. Let's walk through how each piece works under the hood. First, the agent observes the artifact, whether it's a 2D image or a 3D mesh, and extracts pottery-specific cues. If the visual evidence isn't enough, it decomposes the query into targeted search intents and runs an iterative retrieval loop. But before any of those search results enter the dialogue context, they hit source control. This isn't a simple filter, it's a multi-stage curation layer. It starts with validity filtering, checking URL accessibility and text sufficiency to strip out broken links and shallow snippets. Then it scores the remaining hits using a pre-diversity metric that balances query relevance, source quality, and domain priors. To prevent redundancy, it applies a greedy maximal marginal relevance selection, weighting semantic similarity against cross-source diversity and domain novelty. The output is a compact, normalized evidence pool with diagnostic scores attached. You're only feeding the model high-signal, non-overlapping sources. Once the agent drafts an answer, it doesn't just spit it out. It runs the draft through response control. This module decomposes the user's question and the draft response into discrete claim units. It then builds a sparse claim evidence matrix using lexical overlap thresholds to map which claims are actually backed by the retrieved pool. Crucially, it also scans for cross-source conflicts. In archaeology, dating or attribution often varies across publications. The system flags pairs with high lexical overlap but contradictory cues, which triggers a confidence penalty. It then computes a composite reliability score that weighs claim coverage, multi-source support, and conflict penalties. If that score drops below a calibrated threshold, the agent switches to uncertain mode. It prepends an evidence-bounded preamble, explicitly flagging unsupported or disputed aspects instead of fabricating a definitive answer. This is how you get a system that behaves like a careful curator, not a confident fiction writer. Here's where it gets really interesting for inference-time optimization. When you have extra latency budget, VaseMuseum applies a group relative policy optimization approach without touching the VLM's weights. It samples k-independent, controlled trajectories using different random seeds. Each rollout might grab different URLs, cover different claims, or calibrate uncertainty differently. Instead of fine-tuning, it uses lightweight, rule-based verifiers to score each candidate answer on link validity, claim evidence support, neutrality under ambiguity, and conflict awareness. It then picks the highest scoring candidate using a group relative objective. The researchers found that reliability gains saturate around k equals 4, after which the computational cost grows linearly with diminishing returns. So you get significant robustness boosts with minimal overhead, all without gradient updates. To test this, they built an evaluation suite on top of the Vase VQA 3D dataset, which contains over 3,000 ancient Greek vases with structured annotations. They enriched it with the LIMC database for iconographic and mythological grounding, then split queries into 3 categories: visual only, visual plus knowledge, and ambiguous. The ambiguous set is particularly important because it captures underspecified questions or disputed attributions where multiple scholarly interpretations exist. They compared against direct zero-shot VLMs, search-enabled baselines, and ablated versions of their own system. The results tell a clear story. On visual-only tasks, baseline VLMs remain competitive because the answer is in the pixels. But as soon as you add external knowledge or ambiguity, uncontrolled search actually hurts. It spikes hallucination rates and tanks groundedness. VaseAgent flips that. The full system achieves the lowest hallucination rate on knowledge-intensive queries, dramatically improves external link validity, and scores highest on neutrality. Ablation studies confirm the division of labor. Source control is what drives citation quality, while response control is what drives calibrated uncertainty. When they swap the reliability rewards for a pure accuracy objective, Link validity and neutrality collapsed, proving that optimizing for correctness alone encourages overconfident, ungrounded claims. VaseMuseum makes a strong case that for specialized, open-domain applications like cultural heritage, inference-time reliability control is just as important as model scale. By decoupling perception, retrieval, and answer calibration, the system stays modular. You can swap in new knowledge bases or update filtering heuristics without retraining the backbone. It's also highly inspectable, because if an answer fails, the audit logs tell you exactly whether it was a visual recognition error, a weak retrieval hit, or a calibration miss. Of course, there are limitations. The system's performance is tightly coupled to the stability and coverage of external web and museum sources, which can be fragmented in archaeology. It's currently tuned for ancient Greek pottery, and extending it to other artifact types or languages will require domain-specific validation. Future work will likely focus on integrating curated institutional knowledge graphs and scaling expert agreement analysis for reliability metrics. But the core takeaway is clear. When AI steps into domains where accuracy isn't just a number but a historical responsibility, giving it the tools to verify, filter, and honestly say I don't know isn't a limitation. It's the foundation of trustworthy multimodal intelligence. If you're building agents for specialized knowledge domains, I'd highly recommend looking into VaseMuseum's methodology. It's a practical blueprint for making AI systems that don't just answer questions, but respect the evidence behind them.